Hi, this is Chris Fuquay, and this is for College Algebra, Math 1314. This video is for lesson 4.5. Just keep in mind that normally the things that I would write on the board, I have put on this document. So I'll be writing on this as well, but you will take notes just as if I was writing these theorems, examples on the board. So hopefully this will help in understanding 4.5. We will of course be going over this in class as well, but seeing it twice will probably help. So first off, this section covers the rest of the types of different equations that we'll encounter, specifically types of equations that deal with complex solutions. So because of that, we need a theorem that will give us a structured way to understand that every polynomial with a degree n, where n is greater than or equal to 1, has at least one complex zero. This is the fundamental theorem of algebra. So the fundamental theorem of algebra guarantees that every polynomial has a complete factorization if we are allowed to use complex numbers. The number of zeros that a polynomial has is determined by the degree n. If the degree n is greater than or equal to 1, then it has at most n distinct zeros. Those zeros could be complex or they could be real. Let's take a look at an example. So if you notice here, the polynomial for this graph is f of x is equal to negative x cubed plus 2x squared plus 2. Well, based on the degree of the polynomial, the degree is 3, which means by the number of zeros theorem, there are 3 distinct zeros. But looking at the graph, you can see that there is only one x-intercept, or there is only one real zero, which means that that leaves the other two to be imaginary. So in this case, we would say that there is one real zero and two imaginary. But there are a total of 3 distinct zeros. Okay, looking at this polynomial function, g of x is equal to negative 2x squared plus 2x minus 3. You can see that there is a possibility of 2 distinct zeros, but the graph does not cross the x-axis, therefore it does not have any real zeros, which means there are 2 imaginary. So this is a graphical illustration of the fundamental theorem of algebra, along with the number of zeros theorem. Now let's move this to the symbolic aspect, or the symbolic frame of mind that we need to get into. We need to be able to look at a polynomial function in any capacity, whether it's in graphical, numerical, symbolically, and be able to write the symbolic form in both factored form and expanded form. So for this example here, we have a polynomial f of x of degree 3, with a leading coefficient of -3 and zeros for 2i and -2i. So notice that there are 3 distinct zeros. 1 is real and 2 are imaginary. So let's write down our given. We're given that our lead coefficient is -3. We're given that one of our zeros is 4. Another zero is 2i. And another zero is -2i. Therefore, we can write the function in symbolic form as -3, which is our lead coefficient, times x minus 4 times x minus 2i times x plus 2i. And so this is the polynomial in complete factored form. Now let's take that polynomial function that we just wrote in factored form and write it in expanded form. So make sure you have plenty of room on your paper, just in case, because we're going to multiply all this out. Let's first multiply x minus 2i times x plus 2i. Remember, multiplication is commutative. So I'm going to go to the side over here and multiply these two together. Now these are complex conjugates of each other. If you remember, the middle terms cancel. So this is just going to give us x squared plus 4. If you want to do that algebraically to check that, you can, but you're just basically distributing. And the middle terms will cancel. Therefore, you just have x squared plus 4. So we're going to tack that on here. And now next, we're going to multiply the x minus 4 times x squared plus 4. So x times x squared is x cubed. X times 4 is 4x. -4 times x squared is -4x squared. And -4 times 4 is -16. And then writing that in descending order. And then distributing the -3. And we are done. So this is the function in expanded form. The next example here is asking us to write this in factored form. Well, this is an example of when the function will factor by grouping. So if we group the first two terms, and sum that to the last two terms, remember, always put a sum in the middle of your grouping. The common factor in the first group is x squared, and the common factor in the second group is 9. And now we see we have a common binomial factor of x minus 1 So factoring that out leaves us x squared plus 9. And now, since we can factor over complex numbers, the x squared plus 9 will factor. It's similar to the x squared plus 4 above. This factors into x minus 3i times x plus 3i. And so we have complete factored form of this function. Moving on. The next theorem is going to help us even more with this process. It is the conjugate zeros theorem. It says if a polynomial f of x has only real coefficients, and if a plus bi is a zero of the function, then the conjugate a minus bi is also a zero of the function. And this also applies to a square root 0. If you have a plus the square root of b, then you know that a minus the square root of b is also a 0. But that is not applicable here. We're not dealing with just real numbers. We're dealing with complex numbers. So, for example, we want to find a cubic polynomial f of x with real coefficients, leading coefficient -2, and zeros 1 and 2i. So let's write down what we're given, like we did in the previous example. This is going to be a cubic polynomial once again, and our lead coefficient is -2. We have a 0 at 1. We have a 0 at 2i, and based on the complex zeros theorem, that means our third 0 is -2i, because that's the complex conjugate of 2i, -2i. So let's write the factored form. F of x is equal to -2 times x minus 1 times x minus 2i times x plus 2i. Putting it in expanded form, we already know what this equals. Which is x squared plus 4. And now multiplying x minus 1 times x squared plus 4, we get x cubed plus 4x minus x squared minus 4. And distributing the -2. And I'm going to go ahead and write it in descending order as well. So that's 2x squared minus 8x plus 8. And so this is our function in expanded form. Moving on. Okay, once again, leave some room on your paper. This is, it's not a long problem, but it's a process we have to go through. There's a few steps. We see that 1 0 of this polynomial function is given. That 1 0 is I. So based on that, we can find the rest of the zeros, believe it or not. There are 4 distinct zeros because this is a 4th degree, one of which is I. Our lead coefficient is 1. Well, based on the conjugate root theorem, if I is a distinct zero, then so is -I. So we can use this information now to find the rest, believe it or not, because we know that two of the factors are x minus I and x plus I. If we multiply those two factors together, we get x squared plus 1. Based on what we learned in 4.3, we can now use that to break this f of x down even more. And we're going to do that with long division. We can't use synthetic division in this case because we don't have a linear divisor. So we write down the dividend. And now we go through the process of determining what times x squared gives us x to the fourth, and that is x squared, multiplying, subtract, and bring down the next term. Then we repeat the process. Now, what times x squared gives us 2x cubed? Well, 2x. Multiply. Subtract. And bring down our final term. Repeat the process. What times x squared gives us 3x squared? That is 3. Then we multiply. And as you know, we should get 0 as a remainder because of the remainder theorem. And we do. So we know that x equals I and x equals negative I are zeros. Now we need to take this and find the zeros to complete the problem. Well, unfortunately, this does not factor, but we can practice the quadratic formula or we can practice completing the square. Let's practice completing the square this time since it's easy in this case, since we have an even number as a linear term. So I'm going to subtract the 3 to the other side. Take half of b and square it. That gives me 1. This factors into x plus 1 quantity squared. And the other side simplifies to negative 2. Now we take the square root of both sides. And so we get the absolute value of x plus 1 is equal to I root 2. Therefore, x plus 1 equals plus or minus I square roots of 2. Subtract 1 from both sides. So we get x is equal to negative 1 plus or minus I root 2. So the zeros of this polynomial are plus or minus I and -1 plus or minus I square root of 2. Moving on. The next series of problems are just solving. I think that's all we have left. Yep, just solving. So we're going to practice our solving real quick. So just follow along if you would like. Pause the recording and see if you can solve the problem yourself. So we need to set this equal to 0. So we bring everything to the left side. This factors by grouping. Recall that we should get 3 distinct zeros. So let's see what happens. Factoring out the x squared, factoring out the 5. We have a common binomial factor of x minus 2. We factor that out, and that leaves us with x squared plus 5. Therefore, this will factor down a little more. We have x minus 2, and this will factor into x plus I root 5 and x minus I root 5. So if you don't see that, all you need to do is go over here and solve for x. Therefore, the zeros of this polynomial function will be 2 and plus or minus I root 5. Moving on to number 7. X to the 4th plus x cubed equals negative x squared. Once again, please pause this recording to see if you can do this one on your own. Factor out the common factor of x squared. And x squared plus x plus 1 will not factor, and it would be more advantageous or more efficient to use the quadratic formula in this case. So let's use the quadratic formula to solve this polynomial. We already know that x squared equals 0, therefore x is equal to 0. So we have one distinct 0. Now we take x squared plus x plus 1 and solve that by the quadratic formula. So that's the opposite of b, plus or minus the square root of b squared minus 4 times a times c, all over 2 times a. So this simplifies into -1 plus or minus the square root of -3. Which simplifies to -1 plus or minus I square roots of 3 over 2. So we have 4 distinct zeros, even though it looks like we only have 3. Remember what we talked about in class? We talked about how this has multiplicity. This has multiplicity 2. So there's your other 0. So 0 has multiplicity 2, so that accounts for 2 of the 4 zeros. And then the other 2 are here. All right, now this time we're going to practice our synthetic division skills. This will actually solve by factoring, but I want to practice our synthetic division. So we're going to set this equal to 0, just like we would in any case. And now let's write down the factors of P, which should be 1, 3, 7, and 21. And the factors of Q, and this is really easy because it's just 1 plus or minus 1. And so P over Q will basically just be the list of P, because 1 over 1, 3 over 1, 7 over 1, and 21 over 1 is the same set. So the list here of possible rational zeros would be 1, 3, 7, and 21. So let's see what happens. I'm going to pretend like I don't know. I'm just going to start off, and I may guess right. I don't know. I can't remember. I'm just going to say I'm going to try -1. And that does not work because we do not get a remainder of 0. So I'm going to erase. And let's try +1. And that's not going to work. So plus or minus 1 is not a 0. So let's try 3. And that works. So now we have broken this down into we know now that x equals 3 is a 0. And this breaks down into x squared plus 7 because the 0x. And now we can solve this because it's a quadratic. And we don't have a linear term, so we can use the square root property. Which means x is equal to plus or minus I square roots of 7. So there are the 3 distinct zeros of 3 and plus or minus I square roots of 7. Thank you very much for listening to this recording. We got done in about close to 30 minutes, 28 minutes. So we're good to go here. Please feel free to watch this as many times as it makes you happy. But yeah, we will be covering 4.6 next. Thank you once again, and we'll see you next time.